Okay, we're off and running. So yeah, I'm gonna. We're moving on to the next chapter, and the next chapter is power series. But really, this is more to do with radius. It's more to do with the radius and the interval of convergence. Yay. Radius and interval of convergence. That said though, I'm going to start by looking at a power series. What is a power series? So, this is what a power series is generally. So, a power series is something that looks a little bit like this. Like so. So that's a power series. What does that mean? Well, let's just extend the first couple of units. The first term will be A0. The second term will be A1, x minus b to the power of 1, plus A2, x minus b squared, plus dot 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 dot, so on and so on. So that's basically the general form of a power series. One type of power series that you might be familiar with is a geometric series, and that's the next one that they give in the book. So one type of power series, so we'll just write this, one type of power series is this one here. So I'll go the sum from 0 to infinity. Let's go c times by x, and we'll all raise that to the power of k. So this is a type of power series. So what's my first term going to be? Well, my first term will be 1. Thanks, Arthur. Well, plus, what's my next term? Cx, yeah, and then my next term will be plus cx squared plus cx cubed, and of course you'll be familiar with that. It looks a little bit like a geometric series. Well, it is, isn't it? What's the common ratio in this particular one? Yeah, the common ratio in this particular case is cx. So my common ratio r is equal to cx. What will cause this power series to converge? And we did this last year when we did this. Do you remember doing this? What will cause that power series to converge? Is when the common ratio is less than 1. Yeah, so the absolute value of the common ratio, if, I'll just put an if there, if the absolute value of the common ratio is less than 1, then that series will converge. Yeah, it will converge. Good. So what does that really mean in terms of, it means this, doesn't it? That, I just want to bend over, it means that minus 1 is less than cx, which is less than 1. Assuming, of course, cx remains positive, we can just write this. Assuming c is positive, or greater than 1, we can just write this. Greater than 0, sorry. So this series will converge if x is trapped between minus 1 on c and 1 on c. So if I was to draw, say, how do we say, just a line graph of that. Number line is 0. And there, for arbitrary sake, is minus 1 on c and 1 on c. Yeah. When we're trapped between those two intervals there, in here, anywhere in between there, excluding those points there, if that's x, my series will If x lies between those two values, my series will converge, yeah. Converge in there. What we have is we have a special term. A special term is called the radius of convergence. Now the radius of convergence is, does anyone want to have a guess? What logically do you think this term radius of convergence means? Just look at that and have a guess and see what you think radius of convergence means. It's a little bit of a silly term, but it really means, what does the radius normally mean? It means the distance from the centre out to the extreme end on one side and the distance from the centre out to the extreme end on the other side, isn't it? So my radius of convergence is an absolute value, it's always positive. So I hope that that sort of makes sense, that what we actually call the radius of convergence is this value here. It's that value from the middle of the interval out to the extreme value of it. And that's known as my radius of convergence. Yeah? So this represents, well, I'll use capital R, and this is called my radius of convergence. That's called my radius of convergence. And that's out to there. And of course, it's equal on the other side as well. So that's R and that's R there. More generally though, for my power series, what's going to cause this general power series to converge could be three different situations. Yeah? So what values, if you like, what values of x will cause that power series to converge? So what values of x will cause this series to converge? There's a couple of different outcomes. The first of these is one, it could be all values of x. Any value of x could cause the series to converge. Yeah? So one particular case, which we'll have a look at today, is the first one could be, all values of x, element of R, could cause a particular power series to converge, and let's have a look at that. So no matter what value of x you put in, the series is going to converge. Another case is where the series might only converge if you have one particular value. In other words, the series might only converge for one particular value, say b. Okay. So what I'm going to say is and here's my b. So it might only converge for one single value b. And we'll have a look at an example of that. So first of all, it could converge for all values of x. Second, it could converge for one value of x such that x is an for one value of f such that b is an element of R. So it could actually converge only for one value. And then what's the last case, do you think? The last case is this. It could converge for an interval. Yeah? And we'll look at these examples as well. Okay? So the three things that could cause a power series, or the three situations that could cause a power series to converge are, it could converge for every value of x, it could converge for just one value of x, or it could converge over a particular interval. Yeah? So the last one is it could
The second situation same as
No, this is for all that. Well, I should have done this for all values of x such that x is an element of R.
But B is
for one value of x, and that value would be b is an element of R.
就是只有其中一个 x 可以在这上面说，但是只有其中一个 那个 b 不也是所有的？
For instance, I'll show you what I mean. In other words, we could have x minus b is less than 1. So that could be trapped between so I'm just trying to think if x was equal to b. Okay, that's not necessarily a good example to do that. But I will do that over here when we look at this. Just hang on for a second. It could converge over an interval. Yeah. So it could converge over the interval, and this is how we'll define the interval as the absolute value of x minus b less than 1, which means minus 1 is going to be less than x minus b, which is less than 1, which means b minus 1 is less than x, which is less than 1 plus b. What does that mean in this particular case? That what I'll have here is, here's my interval here, and this will be, what am I saying? It's one side, either side of b, isn't it? So in other words, I've got b here, yeah? I've got b here, and then x will be 1 plus b, which is here, which will be 1 plus b, and then this side here will be minus 1 plus b. And my radius of convergence in this case, what will be my radius of convergence in this case? It'll be equal to 1. So in this case, my radius of convergence will be equal to 1. Now, as we'll find out in a moment, this number here is not necessarily 1 because it depends on what type of series that we have. Let's just do an example, and I think through this example you'll be able to see more vividly what I'm talking about. So I might do an example where we look at it could converge over an interval. So let's just do that example first, then I'll go back and we'll look at a few of these ones as well. So can I write this off, and let's just do the example out of the book, and then I'll do the other examples where they converge for all values, where they converge for one value, and then where they converge over an interval. So let's do that now. Right. It'll make more sense, I think, when we just... Oh, sorry. Let me do the first example. For what values of x is that series convergent? In each of these cases, we're going to apply the ratio test. And why is that? Because we want to find out if the series is going to still be convergent, even if we're all the way at infinity. So for these ones here, where we're applying anything to do with radius and interval of convergence, we apply the ratio test. So let's apply the ratio test to this particular problem. Do you remember how to apply the ratio test? Susan? Sorry, Diana, can you remember? Susan's not here, is she? Where is Susan? Can you remember the ratio test? There's the limit. As k approaches to infinity, the absolute value of u
plus 1
divided by
uk.
Thank you. So this is equal to the limit as k approaches infinity of, let's go, we've got x minus 2 to the power of k plus 1, good, divided by, the square root of k plus 2, multiplied by, Vincent? Good. Square root of k plus 1 divided by? Yeah, x minus 2 to the power of k. So that's the easy step, isn't it? Next step, what are we going to do? Let's isolate x's and isolate k's. So, of course you can see here that k plus 1 divided by k, where I've got this to the power of k plus 1, that to the power of k, we're going to end up with just x minus 2. Then we've got to find the limit as, and I'll put this all under a square root sign, of k plus 1 divided by k plus 2. Inside this bracket, I'll divide this by k and I'll divide that by k. So we'll end up with, and I'll take this outside of the limit sign. So I've got x minus 2 multiplied by the limit as k approaches to infinity of, let's just divide by k, so I've got 1 plus 1 on k. Divide this by k, 1 plus 2 on k. And let's take the limit as k approaches infinity, and what does this end up to be? 1. Good. So we end up with this here is basically equal to x minus 2 multiplied by 1. Now, how do I make that converge? What do I need to do to make that converge? I need to let that be less than 1. So, for convergence, so I'll write this down, for convergence, because we're trying to find when it does converge. For convergence, the absolute value of x minus 2 has got to be less than 1. That means minus 1 is less than x minus 2, which is less than 1. Let's add 2 to both sides. So I get 1 is less than x, which is less than 3. What's my radius of convergence, Brian? 1. Very good. A little bit like this example over here, where we had a radius of convergence of 1. This is exactly the same. So let me just draw you that little interval, or that little line graph here. This is 0. That's not 0. That's 2. And either side of 2, Diana, I've got 1 here and I've got 3 here. So inside of this region here, any value of x trapped between 1 and 3 will converge. And my radius of convergence is 1. Should they ask that? So r is equal to 1 and r is equal to 1 in this case. Great. Now, the tricky thing here is, with my radius of convergence is, you'll notice that's easy to do now. Hey, what's my interval of convergence? Do you remember yesterday, or not yesterday, on Friday, when we talked about what causes a series to converge using the ratio test? If it's less than 1, it converges. If it's greater than 1, it diverges. But what if it equals to 1? What if it equals to 1? We don't know. So for that to equal 1, what I'm trying to say is, when this is equal to 1, if you like, we end up with, it could include 1 or it could include 3. I have to do further tests at 1 and 3 to see whether we include 1 or reject 1, or we include 3 or reject 3. I need to find out what my interval is. And this is what I meant by the third condition. So in the last class we talked about, if it's less than 1, it converges. If it's greater than 1, it diverges. But what happens when it equals to 1? We haven't talked about yet. That's because when it equals to 1, I'm examining the ends of my interval. Yeah? They are the ends of my interval. And to define my interval accurately or carefully, I need to see what's happening at the ends of my interval. So, do you know what I do? The first thing I'm going to do is I'm going to let x equal to 1. Yeah? And I'm going to let x equals to 3. And examine both of those ends. So you can see this is a huge problem. A massive problem. The first thing you've got to find is the radius of convergence. Cool. The second thing we have to do is to now examine the intervals, and that's a massive task as we'll see in a moment. Can I just get rid of that? These problems are all the same. And this is one you'll probably get in your exam, because you wait till you see what happens when we investigate the intervals. So let's investigate the first endpoint. So the first endpoint is at x equals to 1. Guys? Yep. Yep, at x equals to 1. So let's let x equals to 1 up here in my power series. Yep. So I'll go up here and I'll say, let's let x equals to 1. If x equals to 1, what do I get? What's 1 minus 2? 1 minus 2 is negative 1. And guess what I end up with there? What's that form, everyone? What sort of series is that? You recognise that straight away as being an alternating series. So in order to test whether an alternating series converges or diverges, what test do I need to use? The alternating series test. You can see why this is a very common problem. First of all, you're testing radius of convergence. You're using the ratio test. Then after the ratio test, what test am I going to now use? Is my alternating series test. So I'm just going to tell my examiner that need to use alternating series test. Now, of course, the reason why I'm doing that is because there are two conditions of the alternating series test. What's the first one? First one, we need to show, we need to show that the absolute value of UK plus 1 is less than UK. So somehow we've got to show the reader that. So the way I'm going to do that is this. I might go this. We'll see if this one will work. So I've got K plus 1 is greater than K. The square root of K plus 1 is greater than the square root of K. And this implies that, of course, 1 on the square root of K plus 1 is less than 1 on the square root of K. Therefore, it's decreasing for all values of K as K. So, therefore, decreasing. And I'll just put a little tick there just to say the first condition is satisfied. What's the second condition? Second condition is the limit as K approaches infinity of UK must equal to 0. That's right. The infinitive term must be 0. So you must be basically adding on 0. So it's going up and down, and gets smaller and smaller. So let's do that test. Righto. We have to test the absolute value of that. We're not interested in the fact it's alternating. So let me go. The limit, black, the limit as K approaches to infinity of 1 on square root of K plus 1, of course, equals to 0. So therefore, my second condition is satisfied. What does that mean? We can now conclude that x equals to 1 is converging. Yeah, so we can now conclude that at x equals to 1 is converging via the alternating series test. Great. One more part still to go. So, what's the other thing we have to check now? Is everyone's x equals to 3. Got to check that end. So I've checked. I know it converges in here. I've checked that end. Yeah. Guess what I can do with that end now? I can rub out that circle and replace that circle with a dot or a closed bracket. Yeah? Can now enclose that point, or if you like, I can put a solid dot in there. Now it's time to examine what actually happens here. So let's go up to x equals 3. If I let x equals to 3, I get 3 minus 2, which is 1, so 1 to the power of k is just always going to be 1. So now I've got a test to see whether the sum from infinity to 0 of 1 divided by the square root of k plus 1, whether that series is going to converge or diverge. And I think you all know that series is going to... What? What's that series going to do, Brian? It's going to diverge. Why? Because of which test, do you think? I would have said the p test. You are right. It looks very, very close to a square root, doesn't it? But guess what? I can't use a comparison test. I'll show you. So that's why this is a great question, really. Really good question. Why? Because if I wanted to use a comparison test, I'd have to show that that was actually greater than the square root of k, wouldn't I? In other words, I could say this. I could say square root of k plus 1 is definitely greater than the square root of k. Yeah? And then we do this. True? Great. Let's put a sum in. Let's put a sum in. Is that helpful to us? Is that helpful to us that this is less than that, given we know this one diverges via the p-test? No, it's not. We can't use a comparison test. So what do we have to use when we know what it is and we know it's close to? We compare to... Yeah, we use the limit comparison test. Yeah? So in this particular case, and I'll just put a little circle around this, because unfortunately I'll put a cross through it too with a dotted line, because we can't use a straightforward comparison. Therefore, we're really forced to use a limit comparison, because we know what the answer is. We've just got to try and prove what the answer is, don't we? We've got to try and prove our solution. So I think we're going to need to use the limit comparison test. We're going to need to use the limit comparison test here, and we're going to compare it with 1 on square root of k. How does the limit comparison test work? We've got to find the limit as k approaches to infinity of ak divided by bk, and show that that is greater than 0. Yeah. Okay. And I'm going to compare that to 1 on k. So let's do that. So I've got the limit as k approaches to infinity of 1 divided by k multiplied by k plus 1 on k. And we've already sort of done that limit, really, haven't we? That's equal to the limit as k approaches infinity of 1 plus 1 on k divided by the square root of 1. I've just divided by k straightforward there. What do we get? The limit equals to? Limit equals 1, and 1 of course is greater than 0, therefore it's going to... Oh, hang on. We know that's going to... Yes, 1 is greater than 0, so therefore if one series diverges, the other series diverges. Yeah? Because this is divergent, that means that's divergent as well. Yeah? So let's conclude. How do we write that? Because, this is a horrible conclusion, but we'll write it out. Because the sum of 1 on root k converges. Yeah, so will the sum of 1 on square root of k plus 1 via the limit comparison test. Just making sure I've got a nice conclusion.
Mr. Stewart, that's divergent.
Thank you. How many times did I say convergent, Brian? A lot? Oh, you should have told me straight away, yeah. No wonder you were going, Mr. Stewart. And I haven't played tennis either. So, what does that mean? What does that mean about this side here? Yeah. So what bracket do we use? Use reverse bracket, yeah. So, in answer to our question, what's my interval of comparison? Let's write the final statement. So my interval of convergence is, what do we say? X is an element of, let's include 1, but let's not include 3. And that's that problem finished. Quite a big problem, isn't it? And that's what we're searching for in all of that. Now, you should be able to go on and do that last question on the assignment, which I asked you to do that, Darryl. Yeah, yeah. Let's do another 3. Can I rub that off? No? No, I'll let you take the photo. Yeah, take the photo. And let's do... This is really the one where I've got an interval. I want to do one where x converges for all values of x, and then x converges for one value of x, and then we'll do another one like this. Sorry, Diana. Righto. We all got that? Can I rub that off now? I hope this is recording. Yeah, it is. Is it in the middle? Oh, I didn't check. It's in the middle. I hope it's in the middle. Ah, it's close enough. Righto, let's go. Rub this off. I've looked at some of this on YouTube, and sometimes it goes out of focus, doesn't it? Have you seen it? Sometimes the whole board goes out. Need a better camera. Okay, let's go to that next chapter. This is the last chapter in chapter 3. We can smell the end is near. 1 chapter to go, and our option is done.
Yeah.
Yeah. You guys must be so tired. Yeah. No. I want to do some more examples, just in case, yeah? Can we just do 3 examples, and then that will probably do. And then that will do, and then we'll come back tomorrow and have a big session tomorrow. Yeah, I think so. Yeah. We can do most of chapter 4 almost in one period. We'll see how we go, in one sit. But let's just do some of these practice problems. So I've jumped right to page 92. Right on page 92, exercise 3C. And I think I've chosen one of each type, one of each problem type. Though, I didn't do these before I came to class, so let's see if we can do them. These are relatively straightforward, I hope. And this one is a little bit more tricky. Right. Brian's off and running. Thank you, Brian. Are you off and running? Okay, same thing. Everyone, what's the question? I've put the problems up, but what's the question? The question is we're finding the radius of convergence. Well, we're finding the interval of convergence, and by doing that, you find the radius of convergence. Agreed? The interval of convergence is really higher order here because it really includes the radius of convergence, doesn't it? But that said, we'll identify that as we're going. What's my interval of convergence here, or what's my radius of convergence? Let's have a look. First step, what have I got to do? I've got to apply the ratio test, so let's do that. Can I write in red? Let's go. K plus 1 factorial. What does this mean? Yeah, it'll always diverge, won't it? So, what's the radius of convergence? There is no radius of convergence. What is it? So the rate R equals to 0. Yeah, no, R 0. The radius of convergence is 0. Why? Because there is no interval over which it will converge. Agreed? So the radius of convergence must be therefore 0. So that's the first case. Do you remember me saying that? Yeah. So this will diverge, won't it? Yeah. So in this case, we have
就是不等于零，就是在问，不等于零。然后等于零的话，不一定是考完这个。
所以那么一定
哎呦我去，
要用回去。
真狠！
稍微别的用什么别的单词？用别的单词。
哎呀，我还有失忆了呢。这应该是，是这个。 哎呀。
so the radius of convergence equals to 0.
然后小于1康，大于1是 I。
What about this one here? What's my radius of convergence for this? It's infinity.
That's when as well we do the interval. We find the interval.
Which one? R is 0, it only converges at x equals to minus 3.
不是那这些玩意儿考试。
Yeah, the radius convergence is 0. Why will it converge at x equals to minus 3? Because I think it's saying minus 3, yeah, minus 3 plus 3 is equal to 0. 0 to the power of k is always 0, except for, is that 0 or 1 in the book? Well, it's just going to converge to, it'll converge to 1. Because 0 to the power of 0 is 1. So, in that case, it'll be 1 times by 0. Oh no, 0 factorial is 1. So that sum will converge to 1. Well, what's the first term? So I've got. Let's actually write that sum out, and you'll see what I mean. Does that make sense? I mean, I didn't see that. Why is that saying this will converge for one value? But it's a strange sort of convergence, isn't it? It's really just this. So we've got this sum is going to equal to, my first term will be 0 to the power of 0. 0 factorial, sorry. Yeah, multiplied by 0 to the power of 0. In this case, that's equal to 1. So my first term is 1. What's my second term? 1 factorial times by 1 to the power of 0. 0 to the power of 1, sorry. Yeah, plus 2 factorial. Yeah, times by 0 to the power of 2. 0 squared is 0. So that's 0, that's 0, that's 0. So really I've got 1 plus 0 plus 0 plus 0 dot dot dot, which of course will converge to the value of 1. It's interesting that, isn't it? So yes, when x is equal to minus 3, that power series will converge to 1. Thank you for pointing that out. I didn't think about that, did I?
所以呢，所以说还得说一个它不等于3。
What's the radius of convergence? So, do you remember I said before that, yes, it will only converge for one value? Yeah.
Oh.
So this is the time it will converge for one value. The radius of convergence will be 0. Yeah. So if I was to draw this on a number line, yeah, if we were to draw what causes this particular power series to converge, then it's just one value, and that value is -3. Yeah. And what's the radius of convergence? 0. It's only one value. And that value is -3. So that's the first situation, isn't it? It converges just for one value. What was the next one? I said it could converge for all values of x. Let's see if that's the case here. Yeah. So we'll check this particular problem and see whether the second problem is the one where it's going to converge for all values. Let's just check that. So we'll come over here. Here we go. Let's apply the ratio test. The ratio test is the limit as k approaches infinity of x to the power of k plus 1 divided by k plus 1 factorial multiplied by k factorial on x to the power of k. That's going to equal to x to the power of 1 multiplied by the limit as k approaches infinity of, this will be k factorial on 1, that'll be 1 divided by k plus 1. Yeah. What's going to happen? Doesn't matter what x is. This is going to equal to 0. So we'll end up with x multiplied by 0 equals to 0. Is 0 less than 1? Of course it is. It doesn't matter what x is. In this case, does it matter what x value we have? No. So this will converge for all values of x. And of course, if you put 3 to the power of k, 4 to the power of k, 5 to the power of k, 6 to the power of k, or whatever, that will still converge that sum. Okay? So, therefore, let's just conclude, therefore, this power series will converge for all values of x. What's the radius of convergence, everyone? What's my radius of convergence in this case? Radius of convergence is infinity. Yeah? So, radius of convergence here can't spell convergence. Radius of convergence is equal to infinity. So my number line just means it will converge for all values. So here's the case where it converges for one value. Here's the case where it converges for all value. And the last one is a good one for you to practice. Now, with this ratio test, with this sort of one where it's an interval, yeah, you'll always get one side of the interval is the alternating series test. The other side of the interval could either be a comparison test, an integral test, or a limit comparison test. So one is always a alternating series test, and the other one's always a bit tricky. Okay? Do you want me to do that with you, or do you want to try and do that yourself? Good for you to try and do it yourself. I'll give you 5 minutes or so, and then I'll do it. See if you can do that yourself. Go. Do you want a piece of paper? Say here. Always forget a piece of paper. Xavier, I spoke to Mr. Wright today about your IA. I've got a copy of that student's IA, which I can give to you. Yeah? It was a good IA, so it's good. But you'll need to do a lot more work on your IA. Anyway, you speak to Mr. Wright about it.
Yes.
You have to work hard in the next couple of days though. Okay. But at the moment I don't think it's a good IA. You need to make some sort of adjustment to it. And I think this could work out okay. Maybe.
Maybe.
Yeah, maybe. Has Mr. Wright spoken to you?
No. Oh no, now one
Got the interval? Have you got the interval yet? Okay. If you've got the interval, I'll start it. I'll start as well. Okay. So I'll come over here and start on this problem.
so much food.
你把啥给我盛进去了？人家在上头呢，再盛底下呢。
哦，哎呦我去！
天呐！
那上面这咋没了呢？啊，知道吗？那上面这咋没了呢？
What'd you give it the radius convergence, everyone?
对呀，它咋没了
2. And I'll just draw a picture. I'll just draw a picture of that so we can have a look at. It's good to draw. You don't need to draw a picture in the exam course, but I just like it. Just helps you to visualise things a bit. Radius convergence is 2. Now I just need to check the intervals now. So I'm going to start by checking when x equals 3. So let me do that. Let's let x equals to 3, so I get minus, so basically what that is, isn't it? It's, if we let x equals 3, it's minus 2 to the power of k divided by the square root of k times by 2 to the power of k, which equals to the sum minus 1 to the power of k on root k.
能不能在中间？能不能懂我脑里面睡了？
I think you can see here that this is definitely, so if we apply the alternating series test, yeah, that's going to be convergent. Yeah. Apply the alternating series test. We're going to have, let's do test 1, which is show UK plus 1 is less than UK. So we'll have 1 divided by the square root of k plus 1 is definitely less than 1 divided by the square root of k. Therefore it's decreasing. Decreasing, and to the limit as k approaches to infinity of 1 on the square root of k is equal to 0. So therefore it's converging. Yeah? So therefore we know at x equals to 3 it's converging. Converging using the alternating series test. Is this making more sense now, everyone? Yeah? And what's the other point we have to check? 7. X equals 7. So we go up here, let's just check x equals to 7. At x equals to 7, we're going to have 2 to the power of k, 2 to the power of k, aren't we? So we're just going to have, really, that's going to reduce, that will be 2 to the power of k divided by 2 to the power of k, square root of k, which equals to the sum of just 1 over k squared, and that's an easy one, isn't it? We can just compare that to, well, that's just a p-test, isn't it? So this one here is divergent. Yeah. This series is divergent because of p less than 1, and therefore my interval of convergence is going to be, therefore, interval of convergence. Can I just do one more thing before we go, if that's all right? Interval of convergence is going to be, what is it? 3 and 7, but we can't include 7. And that's our interval of convergence. Yay! Yeah. Have I made a mistake? No, well, the alternating series test has 2 tests. One, I've got to show it's decreasing, and 2, I've got to show that the limit at infinity is 0. If they both are true, then it's convergent. Yeah, there's lots to remember. Yeah.
Why it will become negative 1?
Good question. Well, because of this, I can take out. I can write minus 2. In fact, I will have it. I'll just write like this. Yeah. So that k will distribute to that, and that k will distribute to that. Yeah. Okay. And then that 2 to the power k is cancelled. Good question, thanks for asking that. Hey, there is one more thing I want to show you. Why is the radius of convergence really important? Why do we sort of worry about this? Well, it just so happens that if we have an integral of a sum, we don't need to write all the sum down and take the integral of every single term. We can actually, as long as we're within the radius of convergence, we can actually integrate the sum and then take the sum of that integral. What is Mr. Stewart talking about? Last thing before we go, right? Can I clean the board? Does everyone understand the three problem types, really? Yeah? The first one I just did, just before I rub this out, let's just do a quick summary. The first one is, this converges for one value, doesn't it? And the radius of convergence is 0. This converges for all values. The radius of convergence is infinity. This one here converges for an interval of convergence, and you've got to check the ends of the interval. Which one are you most likely to get? Yeah, I have never seen that, or I've never seen that. But it's important that we know that, isn't it? It's important that we know those two conditions, one where it's just one value and one where it's infinite values. One more thing I want to show you and then we can go. What's the time? 2:30? 2:50. Well, if we do this, it'd be really good that we just... I just want to show you one more thing. As you can see, these are relatively simple, aren't they? Looks complicated at the start of this lesson, but by now you're going, this is the sort of question I'm going to get on the exam, possibly, isn't it? Because it involves everything. It involves ratio test. Definitely, you have to use the alternating series test once, and then you've got to at least discern which one that you need to use for that last one. I'll just show you one more thing before we go. Can I rub all this off? It's a shame too, but we will. I only need over here. Do you remember that first example I did on the board? I'll show you what it is. This will only take a second. And I haven't really ever seen a question like this before, but you never know. Do you remember this question which we did kind of at the start of this lesson? Was this one here? I'll just write it out so I don't make a mistake. Do you remember that one? I'm not sure if Xavier was here. Who remembers what the interval of convergence for that was? Yeah, you can almost see it, can't you, really? You just take this bit and, you know, it's going to be 3 and 1, wasn't it? But I think when we check the endpoints, we got 1 and 3, like so. Now, if I wanted to take the integral of that sum, as long as I take the integral within the radius of convergence, then I can do something special. I'll show you. Let's take the integral from, I don't know, we can go from, well, what have they done in the textbook? It doesn't really matter. We can go from 2 to 2.5. That's what they've done in the textbook. So I'll just do that, just so we know. Okay, so I'm going to integrate from 2 to 2.5. Now, are those limits on that integration within the radius of convergence? Yes. X is 2, X is 2.5, and guess what? That and that falls within my radius of convergence, or falls within my interval of convergence, I should really say. Agreed? So, if those limits fall within the radius of convergence, then I'll show you a trick I can do. So, if I want to take the integral of a sum, which is quite a tricky thing to do, really, when you think about it. Why? Because what would I need to do? I'd need to write out the whole power series, and then I'd have to integrate every single term by itself. Yeah? And then I'd have to add up all those integrals. That would be quite tricky, wouldn't it? As long as we're within the radius of convergence, guess what we can do? We can swap over the sum and the integration sign. So, and I should put a dx here, of course. Yeah? So this is finding the integral of a sum. If we're within the radius of convergence, guess what we can do? We can change that to the sum of an integral. So I'll just write down, this is basically the integral of a sum. What we're allowed to do, so long as we're integrating within the limits of the radius of convergence, is change this to this. And have I ever seen this? No, I haven't, but you never know. I don't think they'd ask this, but I just think it's interesting nonetheless. What's that now become? That's now become the sum of an integral. Very good. That's now become a sum of an integral. And we could integrate that. How would we integrate it though? Try and integrate that with respect to x. So what do I need to do? I need to add 1 to the power and then divide by 1, wouldn't I? Yeah, add 1 to the power and then divide by, I just have to divide by, divide by k plus 1, wouldn't I? So let's just do that. So we've got the sum to infinity of 0, and let's integrate that between the limits of 2.5 and 2. So I'm going to integrate this. So that will become x minus 2 to the power of k plus 1 divided by k plus 1, yeah, times by the square root of k plus 1. And of course, k plus 1 times the square root of k plus 1 just becomes k plus 1 to the power of, 2/3, isn't it? 2/3, yeah. So let's do that, shall we? And then we've got to put in, x, don't we? So, so let's do that. So that's going to equal to the sum from infinity to 0 of, let's put in this one here first. So 2.5 minus 2 becomes, it becomes minus a half, doesn't it? So it's going to become minus a half to the power of k plus 1 divided by k plus 1 to the power of 3 on 2 minus, let's put 2 in. Of course, if I put 2 in, I end up with 0 to the power of k plus 1 is just 0. So that's just going to be 0. Which leaves, pardon?
The textbook answer is positive 1/2 on the...
No, it is, because the 2.5 minus 2 is positive.
Of course, Mr. Stewart, that's a really bad mistake, isn't it? Is that better? Good. So we end up with, this is the sum of it. Will that converge or diverge? Converge, wouldn't it? Because you've got a half. Yeah, a half, and then you're dividing that by an even smaller number again. That's increasing degree. I would say that's converging for sure. Did you say convergent? What's my first term going to be? My first term will be a half. My second term will be a half squared, then a half cubed. So what's my common ratio? At least my common ratio is a half. Not to mention, I'm now dividing it by a smaller term again. So if it was converging before, because it's just a geometric sequence, if I'm dividing a geometric sequence by an ever-increasing number, it's just going to converge as well, isn't it? A number that's converging divided by an ever-increasing number is just also going to be converging. Anyway, what's the point I'm trying to make? What's the point I'm trying to make just before we shut the video down? Can someone summarise my point? No? Does anyone know the point? The point I'm trying to make is this. If you were to integrate a sum, if you're integrating a sum and you integrate that sum within the interval of convergence, what can you do? You can swap that over and find the sum of the integral, which could potentially be much, much easier to find. Now, in this case, this is not an easy sum to find, right? Yeah. But guess what our next job is? Our next job in chapter 4 is to actually try to see if we can write a function that actually is able to describe this series, and vice versa. In other words, if I've got a function, can I make a function describe a series? Or can I make a series describe a function? And you're probably going to say, Mr. Stewart, what do you mean by that? Well, can I show you something very simply just before you go away? Look at this one here. Ready? 1 minus x plus x squared minus x cubed plus x to the power of 4 minus x to the power of 5. Can please someone write that as sum notation? In sum notation, this would be 0, infinity, minus 1 times by x to the power of k. So I can write that sum as a sum. Can I write that as a function? I can write that as a function. So this is a sum all the way to infinity. Can I write it as a function? What is it? Well, this sum, that sum, is equal to, what's the first term? 1, what's the common ratio? Negative x. So it's 1 minus the common ratio, which equals to 1 plus 1 on x. Believe it or not, that is exactly the same as 1 plus 1 on x, which is equal to f of x. So I've now got a function that represents a series. So our next job is to do two things. Either to write a series as a function, or the more important thing is to write a function as a series. See you later. That's chapter 4.